Okay. Remember the program's available at preregistered.vision, and we're currently just 15 minutes behind. Okay, so the next speaker is Michela Paganini. Michela is a postdoc at Facebook AI Research in California. She previously studied a PhD in physics at Yale, and she co-authored a paper entitled The Scientific Method in the Science of Machine Learning, which was presented at the Debugging Machine Learning Workshop in Machine Learning Models Workshop in ICLR 2019. So thanks very much, Michela.
All right, thanks so much for having me here. As was just said, my name is Michela. I'm a postdoc at Facebook AI Research, where I work on what we call the science of deep learning. And that to me really means trying to bridge that gap that we have between AI and other scientific domains to try to make AI more sound and reproducible and reliable, and really develop a fundamental understanding of what's going on in our neural networks. But my background, again, is in particle physics. So I used to look for new particles at the Large Hadron Collider. So I think I've developed during my PhD, like a real appreciation for pure empirical and observational research. So today, I want to share some of that appreciation with all of you by looking at some of the methodologies that we use in other domains, such as particle physics, and see how we can use that to maybe do better science in AI. So in this talk, I'll go over some nuances of the issue that is at the center of the conversation that we're having today, and then I'll present some solutions that have now become really mainstream in some of their sciences, including but not limited to pre-registration. And then again, I'll draw from my own experience as a particle physicist to tell you more about some of the practices that are common in particle physics. And then finally, if I have the time, I'll end with a quick call to action, if I may. Okay, so let's start with the issue. So I think the issue is that human brains are really good at finding what we want to find. And that might have been evolutionarily very beneficial, but it's certainly not so in research. And so there's this really good quote from a Nature editorial that says, "One enemy of robust science is our humanity, our appetite for being right, and our tendency to find patterns in noise, to seek supporting evidence for what we already believe is true, and to ignore the facts that do not fit." And I think that latter point actually is what we oftentimes call asymmetrical attention. So that is the tendency of questioning analysis and results that disagree with our preconceived notions, but not really scrutinizing those that are already in agreement. And in particular, this ends up becoming very worrisome in machine learning, because we know that neural networks have this tendency of performing remarkably well, even though we might have some horrible bugs in there. So that's a huge issue. And we're oftentimes very quick at finding and fixing issues when the network is underperforming, but not so much when the numbers already look favorable to us. And let me make this clear. This is not to say that this makes us bad people, but it might be making us bad scientists. And so that's what's important. And I think all of us, having been in the field for however many years, we will have noticed there are some striking ways in which these issues come up in machine learning as a field. The reproducibility crisis has been highlighted and documented in the works of many. Most published results, as we know, don't really stand the test of time because the empirical evidence in support of them is brittle at best, and many in the field end up spending months trying to reproduce irreproducible results. And I think this hits graduate students and junior people the most. So that's a major issue once again. So the point is really, if we expect most results and most result sections to be unreliable or cherry-picked, or in general just not statistically significant, then why do we even bother? Like, what value are those sections even adding? And I think many, as we've heard, have stopped reading them altogether. So the reason for that is that, at least partly, there is a strong reporting bias towards results that show that the method that is being proposed works, oftentimes significantly better, not just on par with competing methods. And I think the issue is not just about including tasks where the method has worked and hiding the ones where the method hasn't. There is a more subtle manifestation of this bias, which occurs when we do maybe specify ahead of time the tasks that we are going to benchmark on, but then we continue fine-tuning the models to the point of really overfitting to the validation data, and then ending up reducing the validity of whatever hypothesis we might be testing just to those benchmark data sets alone, and then we lose any power to claim that the method generalizes and works well in general. And then, as we've seen before, there are plenty of methods that probably have worked well, but they haven't been published because they weren't consistently beating everything else out of the water, and we're definitely missing out, I think, on a lot of good ideas because of that. And so I think the perceived lack of progress is really due to a combination of publishing results that are short-lived, as well as the failure of publishing results that are potentially interesting. And there is also a strong recency bias in machine learning that gets us all worked up and working on really just iterations and minor improvements on top of the latest, biggest trends in the field, and that discourages totally novel thinking. So I think we're seeing a lot of that these days in a lot of subdomains of machine learning. But if you let me take a little detour, I think what's interesting is that this historical bias actually takes on a slightly different form in the sciences. So for example, historically in physics, there is evidence that measurements of scientific quantities end up being statistically significantly closer in a very suspicious way to the historical average, as it was known at that time, than to the true value in nature as we know it today. And so that's what you see here, for example, from particle physics on the left. On the right, instead, the positive result bias is really evident in this meta-analysis of clinical trials that compares papers prior and post-implementation of the new pre-registration standards that were implemented by clinicaltrials.gov. And basically what the authors found is that the reports of benefits, so positive results, dropped from almost 60% prior to the year 2000 to less than 10% in the trials published after the year 2000. And the authors also noted that these null results might have been very disappointing for the investigators, but they certainly weren't so for science. And so I think a sign that we're not really doing real science here in AI is that the goal of science is to improve our mental models and our knowledge of what will happen under certain conditions, but if we're still trying with the usual approach of let's try this hack and see what happens, and we aren't able to formulate a hypothesis of what might happen, then we are not making any scientific progress at all. And of course, it can go on and on with anecdotes and data about the perceived lack of thoughtful progress in the field, but at a certain point, the question needs to become, okay, so what can we do about it? What can we do to establish best practices and become more thoughtful and rigorous about our experimentation? And so in a recent work, my co-author and I wrote about the role that the scientific method could and should play in any experimental quest in machine learning that really wants to get at a fundamental understanding of causation and factors of variation in neural networks. And the reasons for the success of the scientific method are, in our opinion, what the values that it's built on. So transparency, falsifiability, reproducibility, and intellectual honesty. So in experimental science, we need to carefully come up with an hypothesis formulation, have clear statements of expectations, a clear experimental design, statistical analysis of results that include uncertainty estimation. So the key missing pieces that we identify in that paper for machine learning are indeed the stages of careful hypothesis formulation and testing, and the careful modeling and accounting of statistical and systematic uncertainties. So first, let's start with the hypothesis. So it's necessary, really, as we've said multiple times, to get past that stage of exploratory analysis and post-diction, and instead use rigorous hypothesis-based prediction and experimentation. And of course, valid hypotheses need to generate logical predictions for what we would expect to observe if those hypotheses were true. And then it's up to us as experimentalists to check and see if we observe those effects, if the effect is stronger or weaker than we expected. Do we even have enough observations to be able to confirm or rule out that effect? And if so, up to what magnitude and with what confidence level? And that kind of gets to the second point. That's the point about uncertainty. We really need to start embracing uncertainty. Experimental outcomes are random variables, so we need to measure their distributions and population statistics, and we can't just have them be represented by a single value that we can fit in a table. So even before we get any experimental result, we should be ready to answer questions like, what are the odds of observing this result if the hypothesized trend isn't real? So what's the magnitude of statistical fluctuations that I could be expecting? Did I just get lucky or unlucky, or is this result potentially statistically plausible? And that's one thing. But then on top of statistical errors, we also have systematic errors. And this can be introduced by any unaccounted for bias in the experimental setup. So every single choice in our experimental design, from the tuning of the hyperparameters to the choices of the data set, can introduce a systematic shift in the results, and we need to be mindful of that if we don't want to fool others, but first of all, ourselves. And of course, estimating uncertainties is very difficult. It becomes more of an art than a science oftentimes, but it's important, I think, to begin developing a culture and expertise around this in the field. So we need to understand what expected variation in our experimental outcomes can simply be attributed to some nuisance parameters, and which experimental variation is instead real and can be attributed to your modification of the neural network. Otherwise, it's impossible to really have any sensitivity to measure any of the quantities that we purport to be measuring. So that's all true and good for all the biases and sources of errors that we can actually quantify and estimate. But what about human bias, which is the bias that we are talking about here with preregistration? And that, by definition, cannot be accounted for like any other type of bias. So we need another type of solutions, and I think preregistration belongs to this family of solutions. And we've already heard about what preregistration is, so I won't go too much in detail into that, but the advantages are clear. So first of all, I think beyond what's already been said, we would have a very thorough paper trail of all of your work at all stages, which makes the attribution and the tracking of the evolution of ideas a lot easier. And so that means more transparency and less folklore. And also it means getting credit for all of your good ideas, not just the ones that end up working right away. And sometimes it really does take months, if not years, if not decades, to accumulate enough evidence in favor or against some hypothesis. And I think the current status quo of publications in machine learning kind of minimizes this issue. And then, of course, as we've seen, preregistration has been shown to improve reproducibility and reduce these unconscious biases. But there are other solutions that belong to that family of solutions, and one of them that I'd like to discuss and focus on is called blind analysis. So at the heart of blind analysis, the idea is that the final numerical result of the study, which could be anything like your final accuracy number or your money plot of whatever kind, should be hidden to the authors until not only the hypothesis, but also all of the methodological, experimental, and analytical choices have been made and frozen. And only then will the researchers be allowed to peek at a numerical result. So before unblinding, researchers need to confirm and agree that every single part of the code has been satisfactorily debugged, every single uncertainty that is quantifiable has been accounted for and reduced if possible, and every single modeling choice has been well thought out, and every single step in the analysis has been checked and scrutinized, so that once the result is revealed, then the authors will be confident that it is correct no matter what it turns out to be. And so it's possible, of course, that in certain cases only after unblinding will you realize that some gross mistake was made, and that's fine. The point of blind analysis is not to force you to publish a paper that is clearly wrong. You can still make modifications, but you should label them clearly that those changes have been made post-unblinding and they could be potentially biased. So how do we do this in practice? So there are a variety of methods for blinding, so to hide these sensitive results. Oops, sorry, my computer tried to reboot. So let me go back to my slides somehow. Okay, we're back. So there is a variety of different methods for unblinding, and this depend on the nature of the data, of the analysis, of the measurement itself, etc. So let me try to enumerate a few of them, and they might work or not work depending on what you're actually doing. So you can first of all hide the total number of examples. So adding or removing a certain number of examples, you can hide the entire data set and only develop your analysis with a simulated data set, or you can add a small fraction of real data on top of the simulated data set. You can shuffle an unknown fraction of your labels during training. You can also simply add a hidden offset on top of whatever quantity that you're measuring so that you don't know what the numerical answer will actually turn out to be. Or you can add a random asymmetry if what you're trying to measure is the comparison between two models or various different models, so that you don't know ahead of time how every single change in your analysis will affect the gap in the performance of these models under a variety of other different topics and other different methods, and some of them we might have to come up with and then be creative about them. So all of these techniques that I've just mentioned are used very successfully in particle physics, for example, and they allow us as researchers to develop our analysis and design our cuts and train our neural networks and whatever we do, achieving the lowest ever uncertainties and the highest ever sensitivity without being biased towards potentially like desirable but ultimately false discoveries. And so what you see here is an example of one of the most widely used blinding techniques that we use when we look for new particles, such as the Higgs boson in this case. So we can have a given theory. In this case, it's a theory that predicts a hypothetical particle, in this case at a mass of 126 GeV, and we can simulate what the histogram of a particular feature, in this case this invariant mass, would look like under the background-only hypothesis, so without this new particle, and the background plus signal hypothesis, so with the new particle. And then when we select interesting events to put into this histogram, it's crucial that we do not look at the data in the region where the signal might occur, because otherwise we might be tempted to optimize our modeling so that the data will show that that new particle actually exists. But if we did that, then nobody would trust our results, and all the millions of dollars that have been spent in building the LHC would have been wasted in some unreliable science. And so what we do is that we pull down this blind, and we use data only where it's safe, so to do cross-checks and sanity checks on our background models, etc., to debug the analysis and all of that. But once we are satisfied, then we submit the blinded analysis for internal review within our collaboration, so that means presenting all of our hypotheses, the expectations, the modeling decisions, the estimates of uncertainty, the attempts to reduce them, and all of that. And only after deep, deep scrutiny and discussion, and when everyone agrees, then we freeze everything and we unblind the analysis and we look to see if the data fits one hypothesis or the other. Okay, so now I've shown you a little bit about how things work in the sciences, so let me get to my call to action. Okay, here we go. So first thing, I think it's really time now to give pre-registration and other techniques of this kind like a real fair shot by creating the right venue, for example, a series of workshops starting from this one, or a dedicated journal or a conference, and we should also be teaching these sort of techniques in schools and really move beyond this thought experiment stage. In addition to that, or alternatively, I think it would be great to see larger research labs or a consortium of research groups get together and establish internal review boards so that we can do blinding and unblinding, and we can keep each other accountable and then maybe raise the standards for the research that we do. And finally, I think we could be thinking about restructuring the field a little bit. So again, taking the example from particle physics, the community there is divided into two, maybe three subgroups. We have theorists, experimentalists, and then in between, if you want, phenomenologists. And experimentalists rarely play theorists, and theorists rarely play experimentalists. So theory papers don't have to contain any experimental evidence for the theory, and experimental papers don't propose any new theory to justify the data. They just contextualize the empirical observations in the context of pre-existing theories. And so the division of labor is very stark and very advantageous, and of course there's plenty of communication between the two communities, but their goals and domains of expertise are very separate. And of course neither can exist without the other, but neither should want to be the other. So we shouldn't expect empirical papers to contain new theories or theoretical papers to contain empirical evidence in support of their own theory, because to me that only leads to very limited and biased experiments from theorists who maybe unconsciously root for their own theory, or very poor theoretical work from experimentalists that are trying to post hoc justify the observations that they made. So That said, the point is that we can learn a lot from the other sciences, and a lot of other people from other domains have been here before, so these aren't unique problems to machine learning, and we should really be widening our horizons. So thank you. Now let's do...
Cool. Do we have any questions from the floor, from Michela?
Yeah. Say that I want to organize a special issue or workshop with pre-registration.
Mm-hmm.
How do I avoid people pre-registering the stuff they already did, experimentally, and now they want to publish it somewhere?
So, okay, so let me get this straight. This only works assuming best intent and real integrity and academic honesty. So I think these are solutions that would prevent unconscious bias that we could all have. Now, if you're a malicious actor, then this is not going to solve that.
Well, somebody has experiments, okay, so
Yeah.
maybe the research is good. But
Mm-hmm.
you want to boost its own standing, and saying, okay, this went to pre-registration, when in fact it didn't. Yeah.
Oh, again, yes, we were certainly not going to catch something like that, even though, I mean, I don't know, you might
Because
eventually
it's
develop an eye for it.
yeah.
You might have an answer to that.
Just something like something of a partial answer is actually if you do that, there's a risk because your paper is going to get reviewed under the assumption that you didn't run any experiments, those that you hid, and the reviewers often will actually ask for radically different things for you to do. So you're essentially just throwing away a lot of work.
Okay.
They're not going to be, in a regular rebuttal in any of these conferences, you have 1 week to respond, so they will try not to have you work too much. It's like, okay, what's the minimal change to make this paper the way I want it? I think it should be. But here it's not like that. The experimental design is still pretty much in flux at that point, which means that I think that's a big disadvantage. Yeah.
Thank you.
I don't know. Whoever.
I mean, if it turns out that the pre-registration reviewers say that it's perfect, then, I mean, that's fine, right, as well. But also, how do you stop the pre-registration reviewers from kind of stealing your idea or being influenced by your idea? Because, I mean, that's kind of subliminal as well, right?
Again, I think like a lot of these ideas, I mean, this comes up in current review as well. Like you can potentially reject a paper and nobody else besides the reviewers has seen it, and the reviewers can go off and write their own paper on the topic. So not that this is a good answer to that, but it could still happen. Yeah, and all of this assumes integrity from the community. So they're not perfect solutions if we don't have at least that understanding. Sure.
So the blinding idea seems like nice and interesting. Do you have any thoughts on how we can maybe practically implement that within the current cycle that we're kind of used to, and how we're submitting computer vision conferences?
Yeah, so I think one of the issues in machine learning is that we use the final number that we were trying to measure, which could be like some accuracy, also as a diagnostic tool to debug our analysis, whereas we should probably be using other metrics such as, I don't know, how the gradients are growing, or I don't know, whatever else is relevant for your, for your domain, to do the debugging without actually looking at the actual number, and always keep the actual number that will go into the final table or plot hidden by inserting some unknown shift. So you actually sample the number from, I don't know, something that contains some noise, and then eventually you undo that. So obviously use computers to help you do that. But that could be one way.
Maybe just one quick question. So given your experience in both communities, do you see any friction or limitation that prevents the machine learning community to adopt self-disciplined protocol like this one, or you think it's just a matter of culture and it can actually be done relatively easily?
In practice, I think it could be done easily, but then obviously there are a lot of social factors that enter the conversation. So unless everybody does it, then the people who do it are maybe initially, especially at a little bit of a disadvantage, because this process actually does take a little bit of time and creativity going through, and it's just, added work. But even as a member of the community, what do you want to be known for? I think, like, for example, the Lawrence Berkeley National Laboratory group, like in particle physics, at a certain point in time was very well known for having hit the right mixture of being able to make really rare discoveries in particle physics without discovering also a bunch of other junk that isn't there, so calibrating themselves to be able to do just the right amount of work, and that helped them build their credibility and put them on the map for who they are today or who they were, especially back then, and I think that helps. So, Philly, maybe?
Yeah,
Opinion? Yes?
Yeah, sorry, just a moment. The suggestion to, actually, it's funny, the suggestion to separate theory from practice. Because it seems like, the theorists from the experimenters not wanting to have both do the same thing because of exactly those biases. And so it seems like it's a very practical suggestion, in fact, because, someone proposes a theory, someone else checks it, so there's no bias there, and vice versa. And you also listed some other ones, a list of some other practical.
Sorry, I don't know where.
How can we develop exactly? So blend analysis methods. So I guess the part where you hide the signal region, you can interpret that for computer vision, for example, as just having a completely given data set, for example, that you can just apply what you developed before, but now just apply it on a different one, for example. Is that
Yes, that could be one way of doing it. Of course, like, again, you'd have to make some special considerations given a new field and new tasks, but could be one way, or you can hide part of the images so that you never know what the final answer would be, and you have the added bonus that you might be robust to occlusion. I don't know. It depends. Those are just some ideas, but I think, yeah, so the separation of domains is kind of a tangential point that has not much to do with blind analysis. You can implement one or the other or both. Yeah.
Thanks very
Cool,
much.
thanks.